In the previous lectures, we talked about a situation where the change in the sample size depended on the current size of the population, right? A larger population resulted in a larger increase. In this lecture, we're going to look at a scenario that's a little more complex. Market penetration describes the number of customers who are currently using or who have purchased a product. And this is often expressed as a percentage, but we're going to focus on the actual number of customers in our model. So how can we model the way market share changes over time? A major source of new customers is existing customers who recommend the product, right? More customers means more friends and coworkers finding out about the product and hopefully purchasing it, right? So if this model holds, then the change in market penetration, delta P sub T, is going to be proportional to the number of adopters at time T. That's P sub T, and I said proportional, right? Okay, in other words, delta P sub T is equal to K times P sub T, right? Where K is a measure of how popular the product is, right? So substituting P sub T plus 1 minus P sub T into that equation, right, gives us this, which we can solve for P sub T plus 1, the next value. P sub T plus 1 equals K plus 1 times P sub T. All right, this makes sense as a starting point, but it's got problems, right? This is a strictly increasing function. In other words, there isn't any kind of upper bound on how large the number of customers can get, which clearly isn't realistic, right? So to fix this, we need to add a factor that inhibits the growth, right? And that caps it at a reasonable level. Let's say our market maximum will be 800,000 customers. And to keep life easy, I'm going to do this in thousands, so we'll call it 800. Right? Where does that number come from? That's the marketing department's job, right? They will hopefully, for an established company, have access to all sorts of historical data, and coming up with that number is a whole different modeling problem, right? So what we're going to do to adjust our model is I'm going to add another factor. I'm going to say delta P sub T equals K P sub T. That's really just our previous model, right? Then I'm going to multiply this by 800 minus P sub T. Right, so what does this do? Right, well, as P increases, 800 minus P decreases, right? P goes to infinity, 800 minus P technically goes to negative infinity, right? Which is just to say it's decreasing, right? More significantly, when P reaches, I keep on writing that infinity symbol instead of an 8. When P reaches 800, our market maximum, what happens to that factor? Well, it becomes 800 minus 800, which is 0. Right? When that factor becomes 0, delta P becomes 0, and the growth stops. Right? Which is what we need to happen. Right? So, making the same substitution, right? Now I'm going to say, what do we have? I ran out of room here, so I'm going to go over to the left. Delta P sub T equals K P sub T, 800 minus P sub T. And then I'm going to make the same substitution that I did here. P T plus 1 minus P sub T equals K P T 800 minus PT, and then we'll solve this, right? Move the PT over. PT plus 1 equals PT plus KPT 800 minus PT. If there's a PT there that you can, P sub T, that you could factor out, but it still leaves a P sub T in there. I don't know that you really gain anything from it. So this is where I would stop, right? This is my new model for this situation, right? That takes into account both the way the growth increases and the way the growth decreases, and eventually comes up against a ceiling, right? So let's take a look at this visually. Excuse me. Take a look at the numeric solution, right? If we start with and remember, this is in thousands, so that's 10,000 customers, right? 10,000 of our best customers, people that we know are influencers in our industry, a bunch of people. Maybe we even give the product away to them for free just to get it out there and to get people talking about it. And then if we start plugging numbers into our model, right, and calculating x sub 1, x sub 2, and so on, and I went out to x sub 15 here, right? This is what we get. And notice what happens out here when we get into bigger n values, right? 705 increased by about 50 there. Then it increased by quite a bit less, right? It increased by just 24. Then here it increased. This is approximate. I'm just doing it in my head, right? Just rounding. Here it increased by only 11, and here it increased by just 3. So we do see that our model seems to be working, right? As time goes on, the growth is slowing down, and as we approach that maximum market size. All right, so what does this look like visually? You notice that's been a trend here, right? Taking data and graphing, looking at it visually is going to be a very common practice for us. And if we do that with this data, we get something like this. And now I think we can really see what's going on. In the early stages, we get very rapid growth up until somewhere around t equals 9, where we reach what appears to be an inflection point, right? And when we get past that point, the growth tapers off, right? And we do appear to be kind of asymptotically approaching this maximal value here, this maximum value, right? This kind of model, rapid growth early on, reaches an inflection point, growth tapers off and asymptotically approaches a maximum. It has a name, right? This is called a logistic model, right? This is seen in a variety of fields, including medicine, where it can be used to model the rate at which drugs are eliminated from the bloodstream and the rate at which an infectious disease spreads through a population. It's used in engineering to predict the probability of a process failing, all sorts of places where this gets used. All right, so now that we've seen some of the different ways we can model change, right, we can start to use this model to answer questions. Right, for example, for a given model, is there an initial value, and a sub 0, that results in a stable solution? That is one that doesn't change over time. Now, this is an important consideration in things like medical models, where we want to maintain a consistent medication level in a patient. And it's important in investing, where we want to get a constant return from an investment. And so that's what we're going to look at in the next couple of lectures.